Next, we want to find a power series representation for the ln of 1 plus x, and we need to find its radius of convergence. So you'll notice it doesn't really look like what we want, but I do know that if I take the derivative of the ln of x with respect to x, the derivative is 1 over 1 plus x, which I know this was 1 over 1 minus negative x. That was, I think, our first example, and it was the sum of negative 1 to the n, x to the n. So in order to find a power series representation for the ln of x, I would like to find the integral of the derivative of the ln of 1 plus x. That is, I take the derivative to get it to look like this geometric setup, and then I take the integral to go back and get it to answer the question. So, do we know what the integral of this is term by term? It would probably be helpful if we write out the terms. So the terms were 1, negative x, positive x squared, negative x cubed, and so on. Right? That's alternating because of that, alternating because of that. So integrating this term by term, I'm going to write the arbitrary constant at the beginning instead of at the end so that I don't kind of lose it in all of this. So the integral of 1 is x. The integral of negative x is negative 1/2 x squared. Then positive 1/3 x cubed, negative 1/4 x to the 4th, and so on. So find a power series representation for the ln of 1 plus x. So there we have it, almost. We've got an alternating sum here, but there's a c, and I don't really care about c. So what I'd like to do is I'd like to know what c equals. I do know that the ln of 1 plus 0, so if we let x equal 0, then I have c plus 0 minus 1/2 times 0 plus 1/3 times 0, and so on. So all of these terms are 0, and then my ln of 1, I know ln of 1 is 0, so c is 0 as well. So what that means is I need to write, from here, I need to write x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the 4 dot 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 in summation form. And I can choose what I want my index, what I want my n to start at. So what I see is I see something like x to the n. I see an alternating sign here. I see a divided by n. So notice it's going, let's go like this. Positive 1 over 1, negative 2 over 1, 3 over 1, 4 over 1, and so on. So here's the, I said that wrong, 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on. So there's my 1 over 1, 2, 3, 4, and so on. Now, what do we have to check? If we start at 1, does this work out? Well, no, because I have the wrong sign here. So I'll just increment that by 1. So now my first term is x to the first, a negative 1 squared, that's a positive 1, divided by a 1, and that gives me my first term. My second term is an odd power of negatives, so that would work out. N to the 2, that works out. Divided by 2, everything's good. So there is my power series representation. Now, this power series representation has an interval of convergence the same as the representation of 1 over 1 plus x. And we saw from the first example that radius of convergence was 1. So this one is 1 as well. Next one, find a power series representation for f of x equals the arctan of x. Well, that doesn't look like 1 over 1 minus something, but we do know that the derivative of the arctan is 1 over 1 plus x squared. So, to find a power series representation, f of x, I could just integrate the derivative. That is, I want to integrate. I don't really want to write this down because you might be tempted to just write the arctan. I want to know what this representation looks like. You know, this seems kind of familiar, like maybe we've written this one out before. Have we done this one before? Wasn't it the sum of negative 1 to the n x to the 2n? So that's one that we did earlier. And now all I have to do is I have to just integrate this term by term. So my first term here was a positive 1. The first term here was positive 1. So 1. Then it was negative x squared. Then it was positive x to the 4th, and so on. So when we integrate this, we're really integrating it term by term, and we get x minus 1/3 x cubed positive 1/5 x to the 5th, and so on. So how do we write that as an infinite sum? Notice that the signs are alternating, so I have a negative 1 to the n. Notice we have an x to the 1, 3, 5. Okay, so that's 2n plus 1, right? Because that gives me the odd powers. And then divided by that same number, so 2n plus 1. Now, this does this give us what we want? Let's try n equals 0 to infinity. Well, yeah, when n equals 0, this gives me a positive for the first term, a positive 1 for the first power, and a positive 1 in the denominator for the second term. When n equals 1, we'll have a negative. We'll have a 2 times 1 plus 1 is 3, and a 3 in the denominator. So that is our power series representation. The last example, asks us to evaluate a power series, evaluate an integral as a power series, and I don't really care about part B. So first thing we need to do is we need to be able to write this as an infinite sum. So we'll do what we've done a couple times now. 1 minus negative x to the 7, like so. So then this becomes the sum of negative x to the 7 to the n from 0 to infinity. So let's rewrite this as the sum of negative 1 to the n, x to the 7n. So what are these terms? The first term's positive. The first term is positive 1. Then we go negative, and it would be x to the 7. Then positive x to the 14, negative x to the 21, and so on. This is easy enough to integrate. It's just power rule here. So after integrating, we're going to have c plus x minus x to the 8 over 8 plus x to the 15 over 15 minus x to the 22 over 22, and so on. Now, I would like to know about the value for c here, if I can find it. Well, actually, I don't care. I take it back. It just says find the integral, and it doesn't give us any information about the initial conditions, so we're going to leave it with c. Can we write this as an infinite sum? You know, we could if we wanted. We could do c plus the sum of what? Negative 1 to the n, x to the 7n plus 1 divided by 7n plus 1. Now, does it make sense to start n equals 0? At n equals 0, the first coefficient is positive. The exponent is 1. That works out. The denominator is 1. So that is our integral.